Okay, welcome to lesson 1.7 on the inverse of the function. Before I get into that, we wouldn't have done a warm-up in class today, so we would have talked about this question here. So you can look at this and just consider what the transformations might be in both of these functions. Okay, so for today's lesson, we're just going to look at a simple question. We looked at this kind of question when we first started function notation. And so we want to look at it again when we're talking about the inverse. So learning target 8 is I know the inverse of a function is helpful if I'm trying to solve for the input and if you know the output. I can find the inverse of an equation, group of points, or a graph by reflecting the graph in y equals x and switching the roles of x and y. So to understand why we use an inverse, we're just going to look at this simple example. So we got a discount movie rental service. I think last time we had downloads. A customer's total movie cost for the year is a membership fee plus $2 per movie. It's sort of dated now, but it could still be like a downloads thing online or something like that. So customer's total movie cost for the year is a function of the number of movies he has rented. So the function would be x would represent the number of movies rented. F of x is the total movie charge based on the number of movies rented. So like that's when we say is a function of the number of movies rented, that's what we let it represent. And so the equation would be f of x equals 2x plus 10. So 2 is the variable cost, 10 is the fixed cost membership fee. Now if we say we actually know what budget we have, so customers grandma put money into account, you want to find out how many movies you can rent based on that. And so so if you have a budget and then you want to find out how much you rent, so in this case, we might sub something in for y and solve for x. So we can actually think of what the equation might be, and we'll talk about it. And so x would actually represent the total budget, and we call it g of x the number of movies rented given the budget. And so that equation would be g of x equals x minus 10 divided by 2. Okay, so we'll talk about how we actually get this. So that gives us a need for a function called the inverse, and it's the opposite or reverse of the original function. And what we do is we switch the roles of x and y, and so we will do it by switching the roles of x and y. F inverse of x, so f to the negative 1 of x is the notation we use. And so we just, when you see this, we mean the inverse. And so I'll ask you to write that as well. Inverse operations, if you take the function, so the way you do inverse operations is you think about the operations you're doing to the input. So in this case, we're multiplying by 2 and adding 10 to the input. And so the way we get the inverse is we just subtract 10 and then divide by 2. So we do the inverse operations in the inverse order, in the reverse order. And so that's where we get what we called g of x before, but now we call f inverse of x. Okay, so we'll actually see how to do it that way, and we'll actually do another way where we switch to x and y. Find the equation of the inverse using inverse operations and switching the variables. So this is a new equation, very similar though. And so for the original function, we multiply by 2 and add 10. So the inverse function, we would subtract 5 and then divide by 2. So notice, instead of multiply, we divide. Instead of add, we subtract. But we also do them in reverse order as well. If you think about what's happening to y, if we balance this equation, we're going to subtract 5 first, then divide by 2. And so that's your equation. Now if you actually want to do it, it's really the same thing, but algebraically we could take y equals 2x plus 5, switch x and y, so x equals 2y plus 5. And the reason why we wrote y instead of f of x is because we were going to switch it, and it gets kind of awkward if you write f of x here. So we're going to subtract 5 from both sides, and we're going to divide 2 on both sides, and so we get y equals x minus 5 over 2, and so really that's the same thing, f inverse. And we do write that notation to, just because this is related to f, so we write the f inverse. We can come back to this example on a graph in a second. Doing another example where we have a square, if we want to do the inverse of this, notice that like this is actually in a transformation form or vertex form, and it has to be in that form so that you can solve for the variable. If you have it in remember from grade 10, standard form or factored form, you actually need this form, so you have to actually complete the square and get it into that form. So using inverse operations, the original function, we actually, if we look at what happened to the inputs, if we subbed a number in here and we wanted to calculate it, what we'd have to do is subtract 1, square it, multiply by 2, and add 3. And so the inverse function, we're going to do the last one first, but subtract 3. Instead of multiply, we're going to divide by 2. Instead of squaring, we're going to take the square root, plus and minus. And instead of subtracting 1, we're going to add 1. And so we get this function here, g inverse of x equals x minus 3, divide by 2, take the square root, and then add 1. And that's going to be the inverse function. Notice that this is a root function with a transformation in it, and the transformation is actually similar to what we did for g of x. We did a vertical stretch by factor 2. Here we do a horizontal stretch by factor 2 because x and y change positions. Here we shifted up 3. This time we shift right 3. Here we shift right 1. Here we shift up 1. So it's just the exact same transformations done on the opposite axis. So by switching the variables, we interchange x and y. So if you don't do it this way, you can do it this way. Solve for y. So we'll move the 3 to the other side by subtracting 3. Divide both sides by 2. Take the plus or minus square root. And then add 1. You get the exact same thing. Looking at our graph, what the inverse is a reflection line y equals x. Since y and x change roles, we actually see a reflection in that line y equals x. This blue line is the line y equals x. It's a slope of 1, y-intercept is 0, so like 1, 1, 5, 5, 10, 10, and so on and so on. That's y equals x. So the graph from A was 2x plus 5, so f of x equals 2x plus 5 with a y-intercept of 5, a rise over run of 2 over 1, and so this red line is the graph of y equals 2x plus 5. So remember that we graph it with a y-intercept and a slope, and the slope is 2 over 1, so go up 2 and over 1. And then to get the inverse, what we actually do is we take every one of these points, so 0, 5, and we switch the order. We do 5, 0. We take this point at -5, -5, and we put a point at, we still have a point at -5, -5, because they just switched. And so really we have a point through here and through here, and so what that graph is actually the graph, the inverse that we calculated. But if you look at it, it's just a slope of 1/2, which is the opposite slope of 2 over 1, and instead of a y-intercept of 5, we actually have a y-intercept of -2.5, which is where we had an x-intercept before at -2.5. That point switched to here, and so every point, just the coordinates switch. So 0, 5 becomes 5, 0, -2.5 comma 0 becomes 0 comma -2.5. And so the orange graph is the graph of the inverse. Notice we just switch every point, and if you want to think about that for a minute, but 0, 5 became 5, 0, -5, -5 stayed -5, -5. And since we knew it was a line, we could just connect that after that. Okay, so if you want the inverse from a graph, we just switch x and y. For B, again, we got the line y equals x. If we graph the parabola that was given, so x minus 1 plus 3, a vertical stretch by factor 2, so it goes over 1 up 2, over 1 up 6. And so we just take each point. So this point here at 1, 3 becomes a point at 3, 1. And so that point should become there. And we still have the same step pattern. So if you watch my mouse, it's going to go up 1 over 2. And so that's exactly what it's going to look like. And so every point in this graph, so you can see 0, 5 became 5, 0, is just flipped in that, or reflected in the line y equals x. And I usually like to do this, although you can't see me turn my screen, I like to turn my head and make sure that we have a reflection in that line. And again, you notice that there is actually 2 square root functions here. So this is the first square root, so that would be a positive square root, and this would be the negative square root. Okay? So one's vertically reflected. Also really interesting, I mentioned this before, if this is a vertical stretch by a factor 2, this one has to have a horizontal stretch by a factor 2 because it's got to be the same shape. And the way we show that horizontal stretch is a 1/2 in here. And so that also backs up the reason why the 1/2 is a horizontal stretch. Notice the -3 is a right 3, and this is up 1. And that's a +3, so it's almost the same thing. This is +3 and right 1. This is right 3 and up 1. So both moving in the positive direction. Okay, and there's some practice.